Hello everyone. In this video we have an example where the controller is in the form of a proportional one with the gain of 1. So GC of S is equal to 1. And we have GP given as 3.165 times 1 minus S over the denominator that we can see here. So basically for this system we have 1, 0 at S equal to 1 on the right half plane, and we have two poles at S equal to minus 0.1 and minus 10. So basically here we will have kind of poles and zeros, minus 0.1 and the other one will be at minus 10. You should pay attention here that we have a 0 on the right half plane, so this is a non-minimum phase system. And I hope you remember that when we have this case on the step response of the closed loop system, we should expect to have an undershoot. So we need to draw the asymptotic body diagram for this system and then compute omega c and PM phase margin from the drawing and verify that the closed loop system is bistable. We can start by forming L of S and then obtain L of j omega. L of S is equal to GC times GP, where we have 3.165 times 1 minus S over 1 plus 0.1 S times 1 plus 10 S. So L of j omega will have these components, 3.165 times 1 minus j omega times 1 over 1 plus j omega over 10 times 1 over 1 plus j omega 10. And to draw the body plot, we can draw the amplitude and then the phase plot for each component separately, and afterwards we just add them to each other. Alright, so here we will go. Let me see if my system is going to respond to me. Here we will have the amplitude of L of j omega, and omega is there. Let me see if I can remove this line that I have drawn. Okay, looks like it's not going to happen. Never mind. Let's start to draw the different segments that we have. The first element is 3.165, which is actually, in terms of decibel, the amplitude will be equal to 10 decibels. Let me just form what we have for the y-axis, 40 dB, minus 20, minus 40, minus 60, and so on and so forth. And in terms of the omega, here we have 1, 10, 100, 1000, 0.1, 0.01, and so on and so forth. So for the first component, which is 3.165, we will have the constant value of 10 decibels. This is 10 decibel. In terms of the phase, I will show you later, but it will be equal to 0 degrees. Then the second component is 1 minus j omega. In terms of amplitude, we will have 0 dB until omega equal to 1, which is the corner frequency, and afterwards we will have 20 decibel per decade for the slope. Then we have the third component, 1 over 1 plus j omega over 10. The corner frequency will be equal to 10. The amplitude will be equal to 0 up to that point. And afterwards we will have minus 20 dB per decade. And finally, we have the last component here, 1 plus j omega 10. The corner frequency is 0.1, so 0 dB until that point, and afterwards we'll have minus 20 dB per decade. Now we can put everything together and obtain the overall body plot for this system. The initial starting point will be 10 decibels up to omega equal to 0.1. This will be the case. Then we have up to omega equal to 1, we'll have minus 20 dB per decade. We will arrive here at minus 10 dB. Then we have 0 dB per decade, and afterwards we will have minus 20 dB per decade. So the black one is kind of the approximate amplitude plot for the given system. And now we'll have the phase plot for the same system. We'll do it for each component separately, similar to what we did for the amplitude, and then they will be added to each other to have the overall phase for the system. So the first one to start with is 0 degrees. That's what we have for the first component, which is the constant value of 3.165. Then for the second one, we have a 0, which is on the right half plane, so the phase that we get from it will be equal to inverse tangent of omega. This will act similar to a pole at the same frequency on the left hand half side. So the phase at that frequency, at the corner frequency omega equal to 1, will be equal to minus, I forgot a negative sign here, it will be equal to minus 45, and at infinity it will be minus pi over 2. So let's say here we have minus pi over 2, minus pi, minus 3 pi over 2, and minus 2 pi. At omega equal to 1, we will have minus pi over 4. 1 decade afterwards, we'll have minus pi over 2. 1 decade before 1, we'll have 0, and this will be the approximate phase plot for that. For the second, for the next indeed component, 1 over 1 plus j omega 10, the corner frequency is 10. So we'll have 0 minus pi over 4 at that frequency, 0 up to frequency of 1, and this will give us the approximate body plot for that component. And the last component is 1 over 1 plus j omega 10. Omega equal to 0.1 is the corner frequency. So this will be the phase plot for that component. Now to obtain the overall phase of L of j omega, we need to add all these together. Up to this frequency of 0.01, we will have almost 0 degrees. Then the phase will start to decrease. At omega equal to 0.1, we will have almost minus 3 pi over 4. At omega equal to 1, we will have almost minus pi over 4, so it will be over here. And at omega equal to 100, we'll have minus 3 pi over 2. Now we can have a look at this and find out the omega c. Approximate omega c will be here, where we have amplitude equal to 0. So omega c will be somewhere around 0.3. We will obtain the exact value using MATLAB. And then at that frequency, we can come to our phase plot and determine the phase margin. So this will give us our phase margin, and to me it looks like it is a bit more than 45 degrees. So phase margin might be bigger than 50 degrees even. We will get the actual value. In order to determine the gain margin, we need to find out the frequency at which the phase becomes equal to minus pi, which is between 1 and 10, and over here this will be our gain margin. So looks like our closed loop system will be stable because the phase margin is bigger than 0. The gain margin is also positive. So the closed loop system will be stable. We can find out the exact values by using the margin command of MATLAB. I have done it and you can see it over here. So for the phase margin, we have it happening. Indeed, we have the exact value here. We have it equal to 88.2 degrees, and it happens at the frequency of 0.316. So for the phase margin is 88.2 degrees, and omega c is equal to 0. Let me have a second look. 316. You can see that since phase margin is bigger than 75 degrees, we can have the first order approximation. And this means that we will not have any overshoot. And our closed loop system is also stable. I also have drawn the step response for the closed loop system. You can see that it is stable, and we have the undershoot over here, which is because of the presence of the 0 on the right half plane. Now we need to find the minimum frequency such that for the closed loop system we have an attenuation of 100 times for the noise signal on the output. Gamma n is equal to 0.01. So this means that we need to find the frequency at which the amplitude of L of j omega becomes smaller than minus 40 decibels. We need to check our amplitude plot, find out where the frequency becomes minus 40 dB. So it's almost there, and the frequency omega n is equal to 330 radian per second. After that frequency, the amount of the attenuation will be more than 100 times. Before that frequency, the attenuation is less than 100 times. Similarly, for the disturbance, we have gamma d equal to 0.01, and we need to find out the frequency omega d. Basically, we need to find out the frequency at which the amplitude of L of j omega is bigger than 40 decibels. If we check the amplitude plot, you can see that the amplitude of L of j omega is always smaller than even 20 decibels. So this is not the case. This will never happen. So we will not have, for this system with this controller, we will not have 100 times attenuation for the disturbance. Finally, we need to estimate the MP and settling time 2% for the closed loop system. As we already discussed, we will have a first order approximation for this system, meaning that MP will be equal to 0, there will be no overshoot, and for the first order system, tau will be equal to 1 over omega c. We have the value for omega c, tau will be equal to 1 over 0.316, and this will be equal to 3.16, I assume. And since we have the time constant for the first order system approximation, we can find out the 2% settling time easily, and you can do it indeed. You can find the numerical value and compare it with the actual value that we have here. You will see that they are not the same as each other, because what we get here is indeed an approximation of the actual value for the settling time. So here we have it close to 6.5 seconds. Alright, so I think that's all for this example. Thank you for watching, and see you in another video later.